right, the last topic in this stoichiometry chapter is on percent yield. I'm hoping that as you've worked through these different sections, you've realized that there is nothing in this chapter that you haven't done before. You should have done everything in chapter 3 in a first-year course. Now, granted, this was pretty much all of third quarter in a first-year chem course, so we're going to zip through it pretty quick because it should be review. So if at any point there's something that's giving you major concerns, that's a red flag to come in and get help, because since this is all review, we're not going to spend a ton of time going through the details of mole calculations and stoichiometry. You've done that before, and you loved it so much that you wanted to do it for another year of your life. Percent yield should be really basic. This is just a way of kind of looking at the accuracy and precision of our lab data. We'll use this most often with lab data. The actual yield is the amount that you actually collected in the lab. This is the number that is based on lab data. This actual yield may include some error. If we've spilled some of our precipitate or we didn't use the right molarity of hydrochloric acid, this actual yield could be flawed. We compare that to the theoretical yield, which is calculated. The amount that we should have collected in the lab. So often when we're looking at lab data together, we can all calculate the theoretical yield. If we all did the same reaction, we should all have the same theoretical yield. But our actual yields will be different. That's where we're going to go with our conclusion. What errors specifically led you to a different percent yield than another group? Percent yield is actual over theoretical. We're going to multiply by 100 to make it a percent. This could be a percent yield of like 100 if you're a flawless human being. 100% yield means that you actually collected 100% of everything that you should have. The percent yield could be above 100 or below 100. Now, most often it's less than 100. Maybe I left some precipitate in the beaker, so my percent yield was only like 90%. I lost 10% of my precipitate in the filtration process. If you end up with a percent yield that's over 100, you've got extra mass. It would be impossible to create more product. The yield that I calculate, the theoretical yield, is the maximum amount of product I should form. But what if your precipitate wasn't dry? Or what if maybe it was contaminated in some way? I might end up with a yield of like 120%, but that extra 20%, that's some kind of outside source. That's adding mass to my product. And then that's what we'll kind of explain when we start writing conclusions. In calculations, we might get something that looks like this. Fun. Methanol is manufactured by a reaction between hydrogen and carbon monoxide. I've got, 68.5 kilograms of carbon monoxide and 8.6 kilograms of hydrogen. We'll always need to calculate the theoretical yield first. And so this is a basic limiting reactant problem. I just don't love that my reactants are in kilograms. So you have a couple options. We have to move them to grams. If you would like, you can just move the decimal spot. Sounds fun. Now, when I move the decimal place, I'm going to try to keep the 3 sig figs. So I could write this as like 68,500 grams. And I'll just leave that without a decimal spot to show that the original measurement had 3 sig figs, and so does this. Or you could put it in scientific notation, and that would be no problem whatsoever. I would have no problem with that. So you could also say like 6.85 times 10 to the 1, 2, 3, 4th. Either's fine. That's the carbon monoxide. And then the other one. Okay, how do I show this one? 3 sig figs your best bet is probably scientific notation. You know, if I move it out of scientific notation, I still want to show that there are 3 significant figures. So I think I'm going to leave this one as 8.60 times 10. This would be times 10 to the third grams of hydrogen, H2. Now, if you would have written this as 8,600, but then when you calculated moles, you left 3 sig figs, that would be totally fine too. I would be all right with that, which is my next order of business. I need to get these out of grams and into moles. 1 mole of carbon monoxide is about 28.01 grams off the periodic table. The hydrogen's diatomic, so the mass will be 2.02. All right, so we'll plug these in our calculator. We're still going to get some large numbers. With 3 sig figs, let's say this is, you could go 2,450. Yikes. Or if you want to keep them in scientific notation, you could say 2.45 times 10 to the third. I'd be okay with that. Either of those show 3 sig figs. And the second one, let's divide by 2.02. So I've got my 8.60 times 10 to the third divided by 2.02. All right, with 3 sig figs, let's call this 4,260. So you could do that, and I would not have a problem with it. You're showing 3 sig figs. Or if you'd like, you can do scientific notation and write that as 4.26 times 10 to the third. I'm cool either way. All right, so now let's see. We've got a ratio in the balanced equation that's not super crazy. 2 to 1. I need twice as much hydrogen as carbon monoxide. And I have numbers, too, that aren't real wild and crazy. So I think this would be a good one to do in our head. Let's do this one by inspection. Let's compare. You can compare either scientific notation or you can compare them out of. If I multiply carbon monoxide times 2, that's the amount of hydrogen I would need. So again, this isn't a crazy number. Approximately 2,450 times 2 would give me about, 4,900 moles of hydrogen needed. Well, these amounts, that's what I have. So just do a quick comparison. Man, I am close. I need 4,900, but I'm just shy. I don't have enough. So that hydrogen will be my limiting reactant. By process of elimination, then, carbon monoxide would be excess. All right. So now we can solve the theoretical yield. Just a little stoichiometry. I always start with my limiting. And we're going to figure out the amount of methanol that should be formed. We go back to the amount of limiting that we have, not the amount that we needed. So let's use the 4.26 times 10 to the third moles of hydrogen, like that. We'll set up the stoichiometry. We'll cancel moles of hydrogen. We'll switch it to our product, the methanol. We'll check the ratio from the balanced equation. It's a whopping 1 to 2. I like to cancel my moles of hydrogen. And then while we're at it, let's go all the way to grams. Okay, so cancel moles of methanol. Let's put her in grams. The periodic table tells me the mass of 1 mole. I'm just going to need to add it up. That's not so bad. You do not need to show work for calculating molar mass. Everything else here, you do. We've got a carbon. We've got a total of 4 hydrogen. And then we've got the 1 oxygen. All right, 32.05. Looks good to me. Moles are gone, so we'll just plug this in our calculator. And it's a done deal. We'll leave 3 sig figs in our final answer. That's a lot. Or 0.26 times 10 to the third. Let's leave this in scientific notation. So how about 6.83 times 10 to the fourth? And that would be grams of methanol. Now, the original problem's got a lot of kilograms up there. So if that bothers you and you would have rather put that in as like, 68.4 kilograms, that would be fine too. They don't specify what unit they want for the theoretical yield, so I'll just leave it as grams like this. Okay, we got the theoretical yield. That's the amount that we should form. Now let's see what our percent yield's going to be. How much did we actually collect? Oh, good. They left this one in grams. 3.57 times 10 to the fourth grams were actually collected. And look for some of those terms too, like this is the actual amount collected or how much should be collected. That's the theoretical yield. Percent yield is actual over theoretical times 100. So we're going to set this up as 3.57 times 10 to the fourth as my actual. Now, they'll always give you the actual yield. In the lab, this would come from our lab data, our measurements. On paper, they have to tell you how much was actually collected. And then we'll divide that by our theoretical, which I should probably go look up one more time, make sure I get it right. Theoretical, 6.83 times 10 to the fourth. 6.83 times 10 to the fourth. We'll multiply her by 100. And then for sig figs, we'll just go back to whatever matches our data. We'll leave 3 sig figs here. So we got the actual divided by the theoretical times 100. I don't know, this isn't the greatest data in the world. How about a 52.3% yield? So they lost about half their product. Now, sometimes that's typical. When you're working with gases, you might not have as great of a percent yield. But then now from here, if this were real lab data, I don't care how bad your data is, as long as you can explain it. So now in your conclusion, maybe you'd say, well, hey, I mean, this isn't the greatest data. We lost about 48% of our product. Well, that's because we accidentally spilled the filter paper with the funnel. Or maybe we accidentally dumped some of the precipitate down the drain. Oh, I didn't filter too great. As long as you can explain it, that's fine. I don't care how bad the data is.